Okay, in this next lesson, you're going to be looking at proportions and work-related problems and solving them using proportions and things like this. We're going to be using formulas in our application problems. Okay, so when we're dealing with proportions and dealing with real-life scenarios, and we have letters that represent things in those scenarios, then we can solve for any one of the variables in that equation. So let's look first at the distance formula. Our distance formula is equal to, we call it D is equal to R times T. Your D stands for distance. Your R stands for rate, and that's how fast you're going. And T stands for the time. How long did you go that? So we can take this equation, D equals RT, and we can solve it for T. So if we solve for T, we want to eliminate the rate, and we'll divide both sides by R, giving you the formula distance divided by rate is equal to time. Okay, or we could solve this equation for R. So we could go back with our distance equals R times T and solve for R. So in this case, you want to eliminate the T from multiplying the R. So we'll divide by T, and that is going to give us D divided by T is equal to R. So as you can see, we can solve for any one of those variables. Thus, when we do this, we end up with three equivalent equations. You have distance equals rate times time. You have time is equal to distance divided by rate, and you have rate is equal to distance divided by time. And the beauty of this is that as we have these equivalent formulas, we can then use them in different ways, and we will be doing that later. Let's look at another one of these equations where you're going to solve for a variable in the equation. Okay? A over K is equal to Q plus X over X. And we want to solve for X. In solving for X, the first thing we're going to have to do is get rid of this proportion by doing cross products. So A times X is AX, and this is equal to K times Q plus X. Now you're going to have to distribute this K, so AX is equal to K times Q plus K times X. Now our next step, since we're solving for X, is we want X all on the same side of the equation. So we're going to subtract KX and subtract KX. And since these are not like terms that we can do anything with at this point, we're going to have to write AX minus KX is equal to K times Q. Now the next step is to factor out our common factor, which is X. So X times A minus K is equal to K times Q. Now we can divide by your A minus K on both sides. Thus, we end up with X is equal to K times Q over A minus K. We can solve for any variable we want in these equations. but they will usually tell you which variable to solve for. In this case, they wanted us to solve for x, and it required us to use our factoring principles to be able to do it. So the factoring that you learned in the last unit, you're using it again now, so you should be getting better at it. One of the easiest applied problems that we have is when you're dealing with a biologist who wants to know whether the populations of deer or fish or whatever are great enough to open the season and permit hunters or fishermen to fish those particular things. So biologists use these proportions to be able to do that. So let's look at this. Biologists tag 2,000 deer. So 2,000 deer are tagged. Okay? Now, what do? 2 months later, they go out and they catch 500 deer. Among those 500 deer, 150 have tags. So what you're looking at here is the tagged deer population compared to the entire population. Okay? So this first one, you have 2,000 tagged deer, and you're comparing it to an unknown total population, because we didn't know the total population here. But over here, my total population caught was 500 deer, and 150 of those had tags. Okay? So now we can use our cross products. 150x is equal to 2,000 times 500 is 10 with 5 zeros. Okay? So now we're going to divide by 150, and we will find out how many deer we had in the original population. And it comes down to 6,666.67. Okay? Or we might round it usually to 6,670 deer. Because these are actually not real super precise numbers. We're not going to mess with fractions of a deer. We're going to round up to the nearest tens or something like that. So 6,670 deer, which is a healthy number of deer, so they would probably open the deer season, because they know that if the population gets too much, the number of deer will kill. Okay. Nurses also use proportions when they're trying to figure out how much dose to give people. Okay. This one says how many milliliters of fluid are required to administer .300 milligrams of a drug if, okay, it is packaged as 120 milligrams in 2 milliliters. Okay, we want 300 milligrams. So we're going to have milligrams compared to milliliters. All right, so 120 milligrams is in 2 milliliters of liquid. So we know that the 2 milliliters contains 120 milligrams. And this is equal to 300 milligrams of the drug. And how many milliliters? Okay, again, cross products, 120 milligrams times 120x is equal to 2 times 300, which is 600. Divide by 120 on both sides, and we end up with x is equal to 5 milliliters. So we're going to have to administer 5 milliliters of the drug to get 300 milligrams. Okay. Okay, this next one is a lot more complex problem. So I'm going to write it up and then we'll... Okay, so let's look at this. This one says, a paddle wheeler travels 10 miles against the current in the same time it travels 15 miles with the current. If the current flows at 3 miles per hour, find the rate in still water. Now I'm going to use a chart to help us do this, but first of all, let's think. What formula are we going to use to find the rate of the boat in still water? Well, it's going to be distance equals rate times time. But which one of those is the same? Is the distance the same? No, one is 10, one is 15. Is the rate the same? No, it can't be, because you're going against the current or with the current, but the rate in still water is what we want to know. And then it says the 10 miles occurs in the same amount of time as the 15 miles, okay? So time is the one that is the same. Therefore, you're going to take your distance equals rate times time, divide by r, and turn this equation into time is equal the distance divided by the rate. So since my time is the same, we're going to have distance over rate in upstream or against the current is equal to my distance divided by my rate, and this is with the current. Okay, because the time is the same. So the distance divided by the rate against the current is equal to the distance divided by the rate with the current. Okay, so let's get that information. 10 miles against the current. So against current, we already know its distance is 10 miles. With current, we know its distance is 15 miles. Now, we need to know what our rate is against the current. The rate when it's against the current is what? Well, it says that the current flows at 3 miles per hour. So, against the current is the rate in still water minus 3 miles per hour. Why? Because it's pushing you backwards all the time. With the current, my rate is going to be my rate in still water plus 3 miles per hour, because it's now pushing you along so you go faster. So now coming back to our formula here, against the current we have 10 over r minus 3 is equal to, with the current we have 15 over r plus 3. As you can see, this is a proportion again. So we're going to have to cross product multiply. 15 times r minus 3 is equal to 10 times r plus 3. Okay, so 15r minus 45 is equal to 10r plus 30. Subtract 10r from both sides, and you end up with 5r minus 45 is equal to 30. Add your 45 to both sides, and we end up with 5r is equal to 75. Divide by 5, and r is equal to 15. So this is going to be 15 miles per hour. And this is the rate of the boat in still water. Actually, I didn't use the chart. I kind of did, though. Let me put that in a chart for those of you who are chart-oriented. Okay. Against current. With current. As you see, I kind of did the same thing. Okay, now we're going to have distance and rate, and then time. Okay, my distance against current was 10 miles. With current is 15 miles. And remember, your time is equal to distance divided by rate. So my rate against the current is r minus 3. My rate with the current is r plus 3. Now, 10 divided by r minus 3 and 15 divided by r plus 3. I don't know which is easier to do, but time, since time is equal, this one is equal to this one. And you end up with the exact same equation, as you can tell, as we had here. But some people find a chart easier to put the information in. So there's a chart possibility for you.